time displacement theorem. This theorem states that if the function f of t is Laplace transformable, Laplace transform of f of t equals to fs, then Laplace transform of f of t minus capital T is equals to e power minus st of f of s, where the function f of t is the function of f of t displaced by capital T. By this theorem, the displacement in time domain becomes multiplication by e power minus st in s domain. Now we have a pulse given, and this function is known as a gate function, and the pulse may be considered to have a delayed unit step function as it's shown here in this figure. Now f of t minus capital T is given by u of t minus capital T1 minus unit function u of t minus capital T2. If you see this, then you are going to get this pulse again, which is a gate function. Now applying the time displacement theorem, then Laplace transform of f of t minus capital T is equals to Laplace transform of u of t minus capital T1 minus u of t minus capital T2. Now this is unit step function whose f of s, or else the Laplace transform, is nothing but 1 by s. Then according to this, the Laplace transform of f of t, that is 1 by s multiplied by the e power minus s, this is t1 here, so t1 minus, here also unit step function, so 1 by s, and we have multiplication factor, that is e power minus s of, here we have a t2. This is our result for this function, that is Laplace transform of the pulse is given by e power minus st1 divided by s minus e power minus st2 by s. Now obtain the Laplace transform of the square wave train as shown here. Now observing the original wave shape, it may be seen that this wave shape can be formed by adding different unit step function and shifted step functions as shown here. Now if you observe here, this is unit step function ut. If you add this minus ut step function to this, then you are going to get a minus ut at this point, and this is minus ut function. Similarly, adding this, you are going to get ut function. So f of t now you can write as u of t minus 2u t minus capital T plus 2u t minus 2t minus 2u t minus 3t, and so on. Now the Laplace transform of this capital F of s equals to Laplace transform of this total function, that is f of t. Now if you observe, we have a displacement function from the second term. By using time displacement theorem, you can solve this, and here we have only unit step function, so 1 by s, minus here we have a unit step function, so 1 by s, that is multiplied by 2, so 2 times, and you have a displacement t, that is e power minus s t, plus 2 times of unit function, so 2 by s, and 2t we have, so e power minus 2t of s minus 2 by s e power minus 3t of s. Now taking 1 by s common, we will be getting 1 minus 2 e power minus ts. Again you can take this common here, then here minus 2 e power st by s is also there, so 1 minus of plus is minus, this is e power ts minus plus here e power minus 2t yes minus e power minus 3 ts plus, and so on. This is the Laplace transform of a square wave train by using the time displacement theorem. Next one, scaling theorem. A scale change is performed to a time variant function f of t by introducing t0 in the time domain where t0 is a positive constant. The new function is being f of t by t0. And the Laplace transform of this new function is given by integral 0 to infinity f of t by t0 e power minus st dt. Now let us solve this, multiplying and dividing with the t0. 0 to infinity f of t by t naught e power minus t naught of s. Here also multiplying and dividing with the t naught, d of d by t naught. Now let t by t naught is equals to capital T. Laplace transform of f of t by t naught is equals to Laplace transform of f of capital T. That equals to t naught 0 to integral f of capital T e power minus t naught s of capital T d capital T. Now, therefore, Laplace transform of f of t by t naught is equals to t naught f of t naught of s. And this term is known as scaling theorem.